What I'd like to do today is kick off this short session on superconductivity at high pressure by focusing on high temperature superconductivity in dense hydrogen systems. This has been a very interesting area of study for the last few years. What I'd like to do is highlight some of the developments in the field and even touch on some very recent work. So the outline of my talk is shown here. I'll start out with some background and context, superconductivity under pressure, dense hydrogen, a little bit of review because this is really the motivation for our work, and then a focus on the superhydrides, some of the materials that we've been working on in the last couple of years, and then even some new developments, some new materials that we've been studying theoretically and are pursuing experimentally as well. So the themes I'd like to develop really are hydrogen in extremes. This is really an excellent example of where computation and experiment have a very, very close synergy. It's this synergy that's made these developments possible in the last few years. And this is also an example of materials by design using high pressure techniques. So a little bit of background. We're interested in materials, matter under high pressure. We're talking about pressures in the range of those found within the center of our planet, at least for the materials that we're studying here. We study a variety of very fundamental transformations. We're interested in looking at kinetic stability and thermodynamic stability of new phases, new structures that can be produced at very high pressure. And here we're talking about pressures in the megabar to even terapascal range, where one perturbs energies rather dramatically. After all, pressure is just a negative volume derivative of the energy. Therefore, pressure is really a knob on which one can use to probe and tune energy landscapes. And really what we're interested fundamentally is really understanding how the periodic table can be understood in this very exotic domain of extreme environments. And I'll come back to this a couple of times. So the experiments involve both static and dynamic compression. I'll focus mainly on static. And here we have a wide range of techniques available to us for looking at materials and quantum materials in particular. Some of the favorite techniques that you have available to you for working at modest conditions or ambient conditions aren't available to us, but we still have a variety of methods we can use to characterize materials in situ at high pressure. And this also involves extensive use of high energy radiation facilities for X-ray, infrared, neutron, and laser sources. And this is closely coupled with computational methods that we do in-house, as well as work with collaborators. And principally, what's made this possible in our area in the last few years in looking at superconductors are advances in structure search methods, but this combined with various methods for looking at the dynamics of systems as well. And I'll highlight all of this as I go along. So pressure effects on superconductors and superconductivity has a long history. It goes back to the very, very earliest days, just a few years after the discovery of superconductivity. The first pressure measurements were made for chemical onus on tin and indium. And for many years, one of the celebrated advances was the very high TC found in this mercury, barium, calcium cuprate with a record TC of 164 Kelvin, and studies of other unconventional superconductors over the years have been very useful looking at pressure effects, and some of those are highlighted here in terms of iron, selenide, and some other related systems. Our interest for many years has been to go to much higher pressure and to look in the megabar pressure range, 100 GPa, and we conducted a number of studies of elements over the years. These are just summaries of niobium, sulfur, and boron using both direct measurements of electrical conductivity as well as magnetic susceptibility, and so finding some surprising changes, for example, in niobium under pressure, but turning materials that were not superconducting, not even metallic, to metallic and hefty superconductors under pressure, such as sulfur and boron. But our focus for many years has really been on element one. So let's start at the very beginning and really look at the first element of the periodic table, the starting point for chemistry, really where we start in looking at many aspects of testing fundamental theory. After all, it's also the most abundant element in the cosmos. And you might view it because of, at least for the proton, its highly quantum character, that we call it the element of uncertainty, which gives rise to a lot of astonishing properties that really manifest themselves at high pressure, as we see in the calculations, as well as emerging from some of the experiments. So a lot of this comes down to looking at the long sought goal of making metallic and superconducting hydrogen, going back to this classic calculation by Wigner and Huntington, and that was followed up by the important calculation, not using computational methods per se, but really more or less intuitive thinking and back of the envelope calculations using basic phonon mediated superconductivity, BCS theory ideas that's suggested perhaps because of the very high Debye temperature. One would have TCs at very, very high temperature, perhaps 1,000 Kelvin, but no specific predictions were made. So just a few comments on the pursuit of that problem, looking at the behavior of hydrogen at very high pressure. This is a phase diagram that summarizes some of the marvelous phases that have been observed up to about 350 GPa. They have all very different structures. And here, theories played a very important role because in fact, it wasn't the ionic phase that I show there at the bottom was actually discovered by us many, many years ago. And it was 20 years later that computational methods basically nailed down the structure. And they also nailed down the structure of this higher temperature phase, which has this really unusual structure that's graphenic. It's called phase 4, and we now understand this to arise from the stabilization of these graphene-like layers of hydrogen in the structure. This prediction was actually ignored essentially by experimentalists for many years, but in fact it was discovered some 5 years after the predictions. So here computational methods were very useful in predicting the structure. We have the constraints on the structure from spectroscopic as well as some diffraction data. But also there are interesting phases that are being produced in calculations. For example, at higher pressure, the possibility of a predicted topological semi-metal, some entirely new physics that go beyond the simple ideas that have emerged in just looking at superconductivity. But is the material metallic at very high PT conditions? Well, this has been an ongoing study looking at the closing of the band gap, going back to early work we did and more recent work. The work that was done by the Harvard group in 2017 showing that about 495 GPa, you have a highly reflective material, and this has been more or less corroborated in my view by the infrared absorption measurements carried out by a French group that showed perhaps there's an abrupt transition. So what has emerged over the years is this idea that one has a sequence of transitions from semiconducting to semi-metallic, but the atomic phase and characterizing it is still a challenge. And here, the exciting aspect of it is really the novel physical properties have been predicted. So here's a phase diagram of hydrogen now on a log scale for pressure. So we're going out to 100 megabars. You can see there on the left, the observed area, and then these predicted phases. And then we have these solid structures, which have these very, very high TCs, upwards of perhaps 700 or more Kelvin at high pressure. Alternatively, there is a different school of thought that says, in fact, you will not have solid phases, you'll have, in fact, a ground state liquid, in which case it would be a superconducting superfluid, some altogether new physics. So a fundamental challenge in physics here is sorting out whether we have superconductivity in the solid or whether we have some altogether new exotic physics in this very high pressure range. It's not yet available to us, but we're very close in experiments. So really what this comes down to in getting to higher pressure is how do we break the bond, the very strong H2 bond in this system. So as you all know, diatomic hydrogen is very strongly bound. It's got 4.5 eV binding energy, a structure or a charge distribution that's largely spherical, so it looks almost atomic-like. Now, years ago, Carlson and Ashcroft proposed various ways of perhaps reducing the pressure or the conditions or producing the insulator metal transition in hydrogen, and therefore perhaps observing superconductivity by impurity stabilization and effectively electron hole pair creation. And so really what this comes down to is populating the antibonding orbitals of the H2 and destabilizing the hydrogen molecule in the solid. So a combination of pressure and chemistry to destabilize this to produce an atomic lattice that may have some of these interesting properties of the pure material. And Ashcroft later termed this pre-compression. So this motivated us many years ago to start looking at ways to dope hydrogen with various elements. We took very simple molecules and mixed them together under pressure and found a wide range of very interesting structures along the way. These are so-called van der Waals compounds, where the molecules are largely intact. We also looked at other systems such as nitrogen. And in each of these, the molecules, or the polyatomic molecules in the case of nitrogen, are intact. And so we don't have any of this bond breaking, at least up to something like 100 GPa in this system. The material there on the right, the H2SH2 compound, in fact, is a precursor of the very high temperature superconductor that I'll come to in a moment. So really the advance in this field in the last few years is the success of structure search methods, which provided guidance to our experiments and targeting particular compositions and pressure ranges. So going to higher pressure and looking at targeted structures turned out to be extremely useful in unveiling some of these very interesting compounds and their properties I'll describe. In fact, here is a list of all these various hydride materials that all came from structure search methods. It started with the calcium H6 structure. This was the one that was really started the field off looking at it because it had a predicted TC of 235 Kelvin. This is the so-called sodalite structure, very hydrogen rich, but there are a range of others with very similar structures. I show here also carbide, replacing the hydrogen with carbon. That was interesting because it shows that in this same very high symmetry structure, the low Z of the carbon also gives it very high TC. And also it's predicted to be stable under ambient conditions, and I'll come back to this in a moment. Well, this motivated our colleagues and minds to actually look for some of these, and in fact, the SH3 or H3S compound was found to be a high temperature superconductor, very high TC with a predicted TC that was very close to what is predicted from simple BCS, conventional superconductivity, and an analog phosphine was also found to have a very high TC as well. Well, we were interested in going to still higher pressures and looking at higher TC materials and taking a cue from the work of Ashcroft and others. We thought we should look for materials with still higher hydrogen content, and we focused on the rare earth systems because we thought they might be a good system to look at in the hydrogen rare earth binaries because of the potential ease with which the electrons could be pressure ionized to stabilize perhaps arrays of atomic hydrogen. So we conducted a number of structure search calculations using the Calypso code from Jilin University. Here I plot the convex hulls showing the stability, and you see over here on the right, on the hydrogen-rich side, very, very interesting stoichiometries, very high hydrides with content of hydrogen 8, hydrogen 10, hydrogen 12 relative to the heavy element for just the yttrium in the lanthanum system. So this is very interesting, and also they have very interesting structures. So here are some of those structures. Those in the middle are more or less conventional hydrides, nothing unusual, but as we go to higher hydrogen content, we find altogether new structures seen here that haven't been observed in calculations or experiment. One that we found was particularly interesting, and by the way, we decided to call these superhydrides, where AHN, or N is greater than 6, would be a separate kind of material to denote the very high hydrogen content. This one turned out to be particularly interesting, this LAH10 and YH10, which is predicted to be stable above 200 GPa. And you can see how it has this marvelous structure. It consists of these 32 atom cages of hydrogen. So it's a clathrate. And these cages surround the heavy element, yttrium or lanthanum in this particular calculation. This is also very interesting because if you look at the HH distances, they're very close to what one predicts for the first phases that form in calculations of atomic metallic hydrogen. That is the first phases you see on compression. So it's perhaps a very good analog for atomic metallic hydrogen. You can also see this in terms of the sp hybridization of those structures. Oh, we calculate the band structure and the phonon band structure as well. Here I plot the phonon dispersion curves where the thickness of the line gives the electron-phonon coupling strength. And when we calculate using very straightforward methods, using the Macmillan formula or Ellie-Ashburn calculations, we can get from these calculations at these pressures for these stable structures, relatively high TCs, in fact, in the vicinity of room temperature. So can we make these materials? Well, I gave this project to a very talented postdoc by the name of Zach Jabal, a very famous last name. He's actually the grandson of Ted Jabal. And he was trained in biology, but we turned him to condensed matter physics, which I believe is in his genes. And he did a marvelous experiment. He mixed lanthanum and hydrogen under pressure in a diamond anvil cell and laser heated it. That is, heated the sample at something like 180 to 190 GPa and found a marvelous change in the diffraction pattern. Also, by just visualizing the sample, you see major changes. You see basically the explosion of the metal sample here as the hydrogen is soaked up inside that structure. And then when you calculate the equation of state, you see this enlargement of the unit cell as the hydrogen is soaked up into that, and there's a rearrangement of the heavy atom sublattice. Well, is it a superconductor? Well, we know now that we've calculated the structure, we have the stability, it's very close to what we predicted, but is it a superconductor? Well, this is an even more challenging experiment because we have to make this sample in a diamond anvil cell with leads to measure, say, conductivity, or coils to measure magnetic susceptibility. We focused on conductivity. And then we have to heat the sample under pressure, not allow for any chemical reactions with the surrounding, including the electrodes. So this is a very, very difficult experiment. We have to prove that we have the materials. We have to do in situ diffraction and then measure transport properties. So when we did that, we found after a series of experiments, we were able to establish that in fact, one has by measuring the conductivity, this conductivity onset that begins at about 260 GPa at something like 190 GPa. There's an offset here in this particular run because the diamonds cracked on the cycling, so there's a slight pressure shift. But it gives evidence for TCs in the range of 260 Kelvin. We reproduced this in a number of other experiments. In this particular one, we actually measured the TC as a function of electrical current, and so we're able to measure the current voltage relation, and we see a difference above and below the indicated TC, which is further evidence for superconductivity. We also looked at this at different pressures and found that if we made the sample at lower pressure, then we had a lower TC. This was actually in agreement with some of our theoretical calculations. And about 5 or 6 months after we reported these measurements, our colleagues in Mainz actually reported very similar results in their studies, using slightly different methods for preparation of the sample and also measuring the effective magnetic field on T. So confirmation of the very high TC in lanthanum H10 from an independent group. So we're quite comforted by that confirmation of our work. So looking at the dynamics in more detail and looking at in more detail at the stability, there's actually a displacive transition in this system on decompression that we noted. We also found that the stability of the phase is somewhat lower than what we predicted using basically our harmonic theory with straight DFT. So we were interested in whether there could be quantum effects or anharmonicity that would be stabilizing the phase and also causing this displacive transition on decompression. So we carried out classical MD calculations and found, in fact, that below the harmonic limit or the stability limit for that phase, one sees stability down to on the order of 150 or so GPa. So it looks like there is considerable anharmonicity in the system that stabilizes the phase to lower pressure. Also, we conducted some preliminary path integral quantum molecular dynamics simulations and found something quite interesting. Even at room temperature, in these calculations, we found that the hydrogen sublattice is highly quantum. That is, it's close to the Lindemann limit in terms of the hydrogen displacements for a classical system. So this is very interesting. So in the range of the predicted and measured TC, it's close to Lindemann. So important because at higher temperature, we found that in fact, the material could in fact undergo full sublattice melting. So you'd have an interesting situation where you might have superconductivity with a fully molten sublattice. We were reminded of work that was done on H3S earlier that showed that 0 point motion in H3S could cause a breakdown in the Migdal approximation. So this gets to really the fundamental mechanism of the superconductivity. This work has been extended in some recent work that was just published, and I believe this will be covered in the next talk. More extended quantum simulations show, in fact, these large basins of stability when you look at the full quantum treatment that goes beyond the kinds of more classical dynamics that we've looked at in these initial calculations. So these efforts continue, and now a large number of groups are looking at superhydrides at these pressures. Here's an example of thorium H10, which has a TC of 159 Kelvin. Praseodymium, this work which is published, has a lower TC, about 9 Kelvin. Yttrium, which was predicted to be higher than lanthanum, is still a challenge, but there's some work that's just come out on yttrium H6 with a high TC of 224 Kelvin, and some work that's been submitted that suggests in a mixed phase of perhaps YH9 and YH10, a TC of perhaps around 260 Kelvin. So in the range of what we found for lanthanum H10, although, as I mentioned earlier, the work done at the harmonic limit suggests that yttrium should be higher than lanthanum substantially. So this may be an example of quantum effects lowering the transition. But the characterization of the yttrium H9 and yttrium H10 is not complete yet. So the story is still not finished, and it's still an open question about whether or not one has a much higher TC in yttrium yttrium H10. So what emerging systematics do we find here? What we find for these materials is materials based on these hydrogen cages, and we have H24, H29, H32. The larger cages give the higher TC. There appears to be charge transfer, as was our initial idea from the heavy element to the hydrogen cage. It stabilizes the cage. Why lanthanum and yttrium as the highest TC along the series of lanthanides? Well, those are the ones that have the highest proclivity for donating electrons to the cages. So with increasing Z across the series, you see a lower TC. For all of these, it appears that the hydrogen sublattice is really dominant here. But again, it's important to look at the full quantum character. And so to really understand the mechanism, one needs to go to a higher level of theory. So this is our current picture of the emergence of hot superconductivity going back to the initial discovery of superconductivity. Here we are around 190 GPa, TCs of 250, 260 Kelvin and lanthanum H10. Again, the mechanism still needs to be understood. We are interested in going to still higher TCs. And of course, the long-term goal is to understand these systems and to develop related systems that could be recoverable to ambient. Well, an exciting prediction for still higher TCs came out a number of months ago, and looking at ternaries, in this particular one, magnesium lithium hydride with a TC of 470 Kelvin. This is basically the same level of theory that gave accurate predictions for the other materials, so it should be taken very seriously.
Russell, I'm sorry to interrupt, but can we wrap up so there's time for a question or two? Or...
Oh, okay, sure.
Sorry.
Okay. I just wanted to mention that in the case of the, in looking for higher TCs and stability, the ternary systems are really the key now. There's a lot of focus on this. And we've actually looked at this in the case of carbon, sulfur, hydrogen, and found an altogether new class of structures, so-called hydride perovskites, that are stable. So mixing methane and hydrogen, or carbon, hydrogen, and sulfur together produces perovskite hydrides, which have very high TC. And finally, looking at oxygen replacing the hydrogen, the sulfur with oxygen, one sees altogether new structures, not interesting necessarily from the standpoint of superconductivity, but from the standpoint of planetary science. You can stabilize H3O, rather similar to H3S. And this, we believe, is actually quite important for the electrical properties, in fact, the dynamo of Uranus and Neptune. So we've come full circle to planetary science. And again, we're still interested in pursuing hydrogen at very high pressure. A lot of work is still underway, both static and dynamic, to look at some of these really novel states that are predicted at much higher pressure using both laser techniques and diamond cell techniques. And I'll close by just summarizing here, without reading, our principal conclusions of this work.
Thank you very much. Thanks for the fascinating talk. Maybe we have time for one or two quick questions, if there are any. Karen, I'll repeat to him in case.
Okay, so I guess you know, this is all amazing and exciting. The thing that caught my eye was the carbon compound. And you know, are there explorations of other compounds with TCs and the arguments that are, on that, following that particular line.
So Karen Rabe was commenting that she noted the carbon-based compounds as quite striking, and are there activities going in that direction or that class of materials?
We are certainly pursuing that. In fact, we discovered this hydride perovskite class of materials by accident in our calculations. What we were really interested in were rigid structures where we could build a framework to stabilize the components of the superconducting material that would be stable under ambient conditions. Instead, we produced these perovskites in the calculation. So we're pursuing both paths to make rigid structures that we can recover to ambient pressure, as well as now pursue some of these other kinds of materials, all based on carbon.
Fantastic. Anything else? Well, let me take the chairman's prerogative not to ask a question, but to relay that recently we had Ted's 100th birthday party. So we witnessed Zach Jabal presenting his work that you referred to his grandfather. So it was quite a special
wonderful. That's great.
circumstance.
We have to bring him back to physics. He's still doing geology.
I see. Fantastic. So if there are no other pressing questions, thanks so much for a wonderful talk.
Thank you.